So I gave you this question at the end of the previous video. Top 10% value. What is the top 10% value? So remember, top 10% value means this area is 10%. Then so we are looking at this point. That makes the area greater than the point is exactly 10% under the bell curve. This means mathematically probability greater than something equals 10%, right? Something greater than something is 10%, but something greater than something, probability greater than something, is not a cumulative probability. So you need to turn this to the other side. Turn the probability inequality to the other side so that probability smaller than the value is 90%. So when you find top 10%, you actually have to use 90 percentile because percentiles are calculated based on the cumulative probability. So probability from the negative infinity up to this point is 90%. That is 1.28, which is equivalent to this, right? So 1.28 is top 10% top 10% value. So top 10% value is actually 90 percentile. So just different ways to describe the same value. Whether you cumulate probability, view the probability from the bottom or from the top, depending on where you see the probability. It's different, but basically they are the same thing. And what's annoying is in statistics is that there are two different notations for each of them. So far earlier we learned percentile based on cumulative probability, but in the later chapters this is a more common notation. I will use lowercase z subscript alpha, which represents the value that gives probability greater than the value equals alpha. So when you have probability alpha, it returns z alpha returns top probability alpha value. So earlier, for example, earlier we calculated top 10% value. Then in this notation, you can write top 10% value as z.1. So it's 10%. 10%, top 10% value is denoted as z subscript 0.1, right? So if you use the CDF, if you use the cumulative probability or the percentile, you have to interpret this as probability smaller than z alpha equals 1 minus alpha, not alpha. So it's confusing and it's annoying, but I don't have power to fix it. So just there are two different traditions that for the same thing. So this is standard notation in statistics. So let's use this. You are going to get used to it pretty soon. Top 10% value. And another good thing about this here is this is always positive. And so top 10% or top 10%, top 5%, top 1%, because you are calculating from the top, it's mostly positive if the probability is not large. If not larger than 50%, the outcome will be positive. So that's the reason why we use top certain percentage in our notation. Okay, and then so again from this information, what is z.05 top? So this is the value calculated probability probability greater than this value equals 0.05. What would be this? You can find a number from this. Okay, Okay, 0.05 is 5%, right? This is 5%. So we are looking for top 5% value. Top 5% is equivalent to 95 percentile. So when you calculate the probability from the top, it's 5%, but from the bottom, it's 95%. So 95 percentile is 1.64, which is top 5% value. The answer is 1.64. Okay, right? That's this is tricky. And then when you calculate the top 5% value, then by the symmetry, it automatically implies that the bottom 5% is minus of that, minus 1.64, right? So top 5% and bottom 5% should be symmetric about 0. So they're just plus minus something. Then in other words, this the plus minus top 5% value contains 90%, right? What I'm saying here is this is top 5%. So 1.64 is the top 5% value, and minus 1.64 is the bottom 5% value. So if you delete these two probabilities, then between these 2 points have an area of 90%. So you can say that, rule of thumb, 90% of the standard normal distribution is contained between plus minus 1.64. It's also, so we are going to use this again. So because in many cases 90% is commonly used number, so you will see that again later. And then because we are using this many times later, we get even more annoying notation. So we are interested in the probability 1 minus alpha lies between something. So here, probability 90% lies between plus minus 1.64, right? But in general, probability 1 minus alpha, say 99%, 90%, 95%, huge probability, close to 1, minus alpha lies between these two. So alpha is the probability outside that interval. And because of the symmetry, if you delete alpha percent, you have to delete half of it from the top and the other half of it from the bottom. So z alpha over 2 is the top alpha over 2% value. So if you cut at that point, then top alpha over 2% is gone. And minus of that is bottom alpha over 2%. So if you cut at that point, alpha over 2% from the bottom is gone. So in that way, alpha over 2 are cut out and trimmed. So therefore, in the end, the probability in between these 2 points will be 1 less alpha. So alpha, each tail is trimmed by alpha over 2%. This is the reason why I'm talking about this is because we are going to use this later. So this chapter is more about more preparation for what we are going to see later, which will be more complicated. We have to learn a lot later, so I want you to get used to them earlier. Okay, so far we have considered the basic ways to calculate probabilities or the values implied by the probabilities, right? So, and the idea is Excel. You use Excel and a little bit of manipulation. But the manipulation is pretty simple if you understand the symmetry and the bell curve, and if you understand the probability is an area. So it's just about area. So like uh, so once you know you have the number, when if you calculate the numbers from Excel like using like this, then on like the intuition can be obtained from the graph. Okay, this is how we utilize the standard normal distribution. So far everything is based on the standard normal distribution. The CDF based on CDF of the standard normal. But what if the parameters are different? We have to think about that more carefully. So if you have different mean and different variance, then how can we calculate the probability, or how can we calculate the percentile? We are going to study the process of standardization. So those non-standard normal distributions will be standardized. And they can be fit into the standard normal distribution. So from the standard normal distribution, any normal distribution can be calculated. And what we need in that process is this result. You may remember we learned these results in chapters 3 and 4. So at that time, we considered a linear transformation given by this. So you have x, and if you multiply a and add b, you get another new random variable. Then what is the relationship between the mean and variance and standard deviation of x and y given by this? So the mean preserves the same relationship. The variance is not affected by the additive number, but the multiplication is squared, which is annoying. So standardization standardized it again by taking square root. So standard deviation is affected by the multiplication, not by the addition, right? So we got these three things. Then how can we use this? Whatever normal distribution you get in X, I would like to make I'd like to transform the non-standard normal distribution X into another random variable, but the random variable will be a standard normal distribution. That is, if X is normal, then Y is also normal. This is a very powerful property of normal distribution. This property, so this, you may think this is obvious, but actually it is not obvious. For example, if you replace normal with binary or binomial, it's not true. So if X is binomial, then AX plus B is not binomial. It's not guaranteed to be, there is no guarantee that AX plus B is binomial. So many distributions do not satisfy this kind of nice property. So it's another reason why we are using the normal distribution. And then think about this. We have normal distribution, and then so X is non-standard for general mu and sigma squared. And if you have X like this, and then we know the parameters for Y, because we know how the mean and the variance of Y are going to be determined, like according to our formulas, results we obtained earlier. So Y is another normal distribution with this mean obtained by this, and variance obtained by this. So those two parameters fully specify the distribution of Y. And we are going to deliberately choose the numbers A and B so that the new random variable has a mean of 0 and a variance of 1. So then how can we make the new variable standard? that it's simple. If you use A equals 1 minus sigma, then variance will be 1. So if you think about this, 1 minus sigma, like 1 over sigma in the place of A, then automatically it will be 1. And then B is B should be minus mu over sigma. And then it is easy to see that this will be always 0, right? If you plug in this A and B, the mean and the variance will be always 0 and 1. In sum, our new random variable y looks like this. Y in the end is there is a original variable x. First, recenter, subtract the mean so that the center is adjusted to 0, and then divide that by sigma, which is the standard deviation. Remember, it is not sigma is standard deviation, sigma squared is variance. So you divide the x minus mu by standard deviation. And then, so it's like if the variability was large, then you reduce it by dividing it by sigma. If the variability was small, then it will standardize to 1. So subtracting mean dividing by standard deviation is the process of standardization of normal distribution. And then we are going to use z. Remember, z is the notation for the standard normal distribution. Usually so we call this z-score. X is standardized, and then the standardized random variable is usually denoted as z, and it is standard normal distribution. Then you may interpret z as this way. Z is standard normal distribution. So 95% of z takes is between plus minus 2. So if z equals to say plus 1, what does it mean? Its meaning is that if z is 1, that means that observation is 1 standard deviation above the mean in the original distribution. In the original distribution, the mean can be any number. The variance also can be any number. So we recentered it to 0 and rescaled it to 1. So then z measures the distance from the center in terms of standard deviation. That's how we interpret the standardization. And if x is above its mean, z is positive. If below mean, then negative, which is obvious. So we are going to use this standardization, and I will give you examples and examples to see how to use the methods to calculate the probabilities for the standard normal distribution. Apply that methods to non-standard normal distributions. We are going to learn that next week. I will continue that in the next week. And the next week, my plan is to finish chapter 6 and start chapter 7. Do a little bit of chapter 7. Okay. Good luck and see you later. Bye.